We look at control of diesel engines, and I believe that you have already had some lectures on combustion in diesel engines, so we will not go too much into combustion, so we'll continue to control. So if you look at the main features of a diesel engine, I'll quickly go through this. We know that it has a high thermal efficiency, it's a highly reliable system, it produces high torque output, it has problems of NOx emissions, smoke and particulate emissions. It emits high noise levels, and it also can produce high vibrations. So basically, if you want to improve a diesel engine, we'll be looking at these problems, and I think what we are going to see today is how the engine can be managed to mitigate some of these problems. Now, the stages of combustion in a diesel engine, I believe you already have been told about this, but I'll briefly go through this. So the diesel engine combustion starts with fuel injection. We know that we take air alone, we compress this air to a high compression ratio, and the temperature goes up to fairly high levels, and then we inject the fuel, and this fuel is injected as a fine spray, and the moment it is injected, it doesn't burn. So it stays in the combustion chamber for some time, and this period where it stays in the combustion chamber without burning is called the ignition delay, and this ignition delay can be broken into two phases. One is physical and the other one is chemical. The physical portion involves all the physical aspects like atomization of the fuel, dispersion of the fuel, then its penetration, vaporizing, mixing with air, and getting ready for combustion, even getting heated, its temperature being changed and all that. And the next portion is the chemical portion, which is supposed to follow the physical portion. And here we start the chemical, here the chemical reactions start and they become self-sustainable, and the combustion reaction becomes active. And this is highly temperature dependent. In fact, both are temperature dependent, but the chemical phase is highly temperature dependent. And these two delay periods may be something like 1 millisecond or less than 1 millisecond in a diesel engine. And following this ignition delay, you have a phase which is called rapid combustion phase or the premix combustion phase. We'll see it very soon because it is very relevant to the engine management system. And following the premix combustion phase, we have the diffusion controlled combustion phase or the mixing controlled combustion phase. And finally, we have a tail burning phase or the after burning phase. So these are the different phases of combustion in a diesel engine. So if you look at the diesel engine, the first portion of heat release after the ignition delay is called the premix phase, and in the premix phase, combustion starts with a high heat release rate. That is, combustion is sudden. And following this, the fuel gets injected as the burning occurs, and the temperature and pressure further go up, but combustion is not so sudden. It's not so rapid. And in the second phase, the burning of the fuel depends on the rate at which you can mix the fuel and air. So I believe all this is already known to you. So I'll just come back to this. So this shows a typical heat release rate curve. On the x-axis, if you see, you have the crank position, and the y-axis you see, you have the heat release rate given in joules per second or watts. Sometimes people write it even in terms of joules per degree crank angle. Okay, so but what is important is the rate at which the heat is released is being shown. The curve that you see here is the heat release rate curve, and the curve that you see here is actually the fuel injection curve. This is fuel injection and this is the heat release rate. So first let us look at the fuel injection curve. The fuel injection curve is basically indicating the milligram per second of fuel. That is the rate at which the fuel is being pumped into the engine. So this is TDC, top dead center. Before TDC we start our injection, and suddenly injection starts occurring, and it lasts for some duration. And this I call as the start of injection, SOI, start of injection, and this we'll call as duration of injection. So start of injection and duration of injection. So combustion, the injection starts and lasts for some time. This duration of injection could be something like in a normal diesel engine. I'm not talking about electronically controlled diesel engine. It could be something like 30 degrees or so of crank rotation, which can translate to something like about sometime between 1 and 2 milliseconds. So, and you find here that combustion starts somewhere here. This is start of combustion. Combustion does not start immediately after injection, and there is a small gap, and this gap we call as the ignition delay. This gap between start of injection and start of combustion is called A, and this A is ignition delay. So between start of injection and start of combustion there is a lag, but you should understand that during this lag period fuel is still being pumped into the cylinder, and this fuel which I showed in the shaded as shaded is actually fuel that is being pumped into the engine, but it's not burning. It's simply staying in the engine, and whatever is staying is mixing with air and forming a combustible mixture. So at the end of the ignition delay period, this mixture which has been accumulated suddenly burns. It is like explosion. This is what is called as diesel knock. Diesel knock occurs just because the fuel that is accumulated during the delay period mixes well and burns suddenly. So you find that there is a sudden rise in heat release rate. So suddenly the heat release rate shoots up like an explosion, immediately falls down. When all this is burnt, it falls down. But fuel injection is continuing. So the fuel that comes after the start of combustion is coming into the cylinder at a high temperature. The temperature of the cylinder has already gone up, so it's now entering at high temperature. So this fuel does not suffer a big ignition delay. So as it comes, it tries to burn. So the burning rate at which the fuel can burn actually depends on how well the fuel can mix with air and produce a mixture. So that is why we call it the mixing controlled combustion or a diffusion controlled combustion. So we see that this is the first box is a premix phase, and the second box is the diffusion combustion phase. So the diffusion combustion phase is a long phase, and it burns without any delay, but it burns at a rate which is determined by the air fuel mixing, and the first portion is dependent entirely on ignition delay. Now the most important thing that we have to note here is what are the implications of these two combustion phases on the performance of the diesel engine. Now the first phase gives you sudden combustion. Sudden combustion is always good from the point of view of efficiency because it is like constant volume combustion. So first phase is good for efficiency, but first phase produces a lot of noise because it's something like an explosion. So the premix phase produces a lot of noise, gives good efficiency, and also produces a lot of vibrations, and it also produces high temperatures because it's a sudden explosion. If you look at the second phase, it is slow, it is not so fast, it is controlled. And the second phase, you don't have noise, it is smooth combustion, but you don't have very high efficiency also because it is slow combustion. And the second phase, the other problem is you are not giving sufficient time for the fuel and air to mix. So in the second phase, the fuel has to find its air, mix and burn, and if it doesn't find its air, the fuel will burn with insufficient air, and if it burns with insufficient air, you can have hydrocarbons, carbon monoxide, and very importantly soot. So this phase can give you soot, HC, CO, and efficiency generally in this phase is not very high. So that's what is written here. Diffusion controlled combustion gives you smoke, HC, CO, and low efficiency. Premix combustion phase gives you noise, NOx, but is good from the point of view of efficiency because it is fast. So now if you are and the premix combustion phase is heavily dependent on the ignition delay. If the ignition delay is long, premix combustion phase becomes very high. Suppose I have the fuel injection started here and the ignition delay becomes long, then the premix combustion phase would have gone like this, and the diffusion combustion phase would have gone like this. So it would have changed. The premix would have become still important because more fuel is accumulated during the ignition delay period. So one way to control the premix is to control ignition delay. If you reduce the ignition delay, premix will come down. Increase, premix will go up. So one can play with the ignition delay to control premix, but ignition delay is very difficult to control. So it is not a parameter which can be controlled. On the other hand, the diffusion controlled combustion phase depends entirely on mixing. It is how well the fuel can be mixed with air. So if I mix the fuel rapidly with air, diffusion can become better. You can raise this diffusion combustion phase if you mix the fuel rapidly with air. So there you can do something with the injection system. If you inject the fuel with a high pressure, fine droplets, then diffusion can become better. So if you look at all these things, if I summarize everything, premix is good from the point of view of efficiency, but bad from the point of view of NOx, noise, knock. Diffusion is not good from the point of view of efficiency, but good from the point of view of noise and all that. Diffusion gives smoke, premix does not give smoke. So you cannot say that I want only premix, I want only diffusion. Both have their good and bad points. So the engine management system has to mix both of them to the right level and get good efficiency and low emissions together. So that is what the engine management system does. So what the engine management system actually does is tries to bring down premix little bit. It tries to bring down the premix and tries to improve the diffusion. So we are trying to bring down premix and improve the diffusion. Now how can you bring down premix? How can we bring down premix? Reduce ignition delay, but I told that ignition delay is a parameter which is linked to the fuel and all that, so it is not so easy to reduce ignition delay. Maybe you can reduce to some extent by using very high pressures. If you atomize the fuel finely, then the physical part of the delay will come down, but significant reduction is not possible. So what people do is, they don't inject the fuel like this. If you look at, I draw again this fuel injection curve alone in milligram per second versus crank angle. What I drew earlier was something like this. Fuel injection starts at some point and goes at some value and then stops. Instead, if we draw something like this.
Now, what they have started now is they are spraying it in stages. Now, the first generation CRD fuel supply systems and the next generation fuel supply systems, they have also a lot of difference.
Yes. Yes.
They are in intermittent stages. Fuel is made in intermittent stages. First stage, the quantity is more, then the quantity gets reduced, then it further gets reduced. It is in 4 stages nowadays.
Yeah, we are going towards that. In fact, I'll be explaining that. We'll be going there. So, what we actually do is, we first inject at a small pulse, we stop the injection, and then we again start and inject. So, let us say we do like this. So first you inject and then stop. Then what happens is, we stop the injection somewhere here itself. So the amount of fuel that is staying inside the cylinder during the ignition delay period is becoming small. So at the end of the ignition delay period, only that fuel will burn. So the premix will come down. And after the premix combustion starts, you start pumping the fuel once again in the second phase, and there you pump it so that the diffusion combustion can be efficient. So this is the modern diesel engine. This is the way in which the modern diesel engine is controlled. So you basically have to split your injection into 2 parts. One small part right at the beginning, which is injected in such a way that the amount of fuel that accumulates is very small. Stop the injection there. We call it as pilot injection. The first one is pilot and the second one is called main. So pilot injection, the role of pilot injection is to start the combustion process and raise the temperature in the cylinder. And the second injection, which when it comes, it faces hot gases, so its ignition delay is low and it's only diffusion combustion. So
what is this second phase called?
It is called the main injection.
Main injection. Okay.
Main injection. Yeah. The first injection is called pilot injection. Okay. Yeah. So the second injection and the first injection both occur at high pressures. The first and the second injection occur at high pressures. And what is the benefit of using high pressures? These high pressures can give you very good atomization, and very good atomization can ultimately end up in very low, very good diffusion combustion phase. So if you increase the pressure to something like, let us say, 1000 bar, we are looking at a jump in pressure. The earlier diesel engines were working at pressures of something like 400 bar, 500 bar. The injector opening pressure is 200 bar, injection pressure could be some 500 bar. But now the trend is to go to 1000, 1600. People are looking at beyond 2000, some people are looking at 3000. 3000 bar and all is an unimaginable pressure, if you can really see. 3000 bar, if you convert to meters of water, you just try to convert and see, it is 30 kilometers of water. 3000 bar, one bar is 10 meters of water. So you can convert 3000 bar and see, it is 30 kilometers of water column. So such pressures, and in a normal diesel engine, now common diesel engine, it is very common to have something like a pressure of 1500 bar. That means you are operating at extremely high pressures. pressures which are greater than the pressures which are used for water jet cutting. In water jet cutting of metals, I think they use pressures of the order of 700 bar like that. But in the diesel engine, you are using already some 1500 bar. So it is an extremely complicated system with very high pressures. Even a small leak can be really disastrous, because if something leaks, it can virtually cut. If there is a spray coming out and if we put our hand, it can actually cut through the hand. So it is a very complicated system. And why we use such high pressures is to actually boost the diffusion combustion phase. We want to raise this diffusion combustion phase, and for that we need high pressures. And we do not want to boost the pre-mix combustion phase, so use a pulse. So a minimum is 2 pulses, but there could be, as someone was now pointing out, there could be even 4 pulses, there could be 5 pulses. In a HCCA engine they use even 8 pulses. So we could have many pulses. So the modern, so let us go back to the original problem. The problem is to inject in pulses and see to it that we are able to bring down premixed and see to it that we are able to enhance diffusion. Both are the aims of any modern fuel injection system. And the problem comes because of the short times. To give you a feel for the time, we were looking at SI engines where we had about 10 milliseconds for injection. Then GDI engine where we have something like 1 to 2 milliseconds for injection came down. Whereas in the diesel engine, the first injection could be something like 200 microseconds. So we have gone down in scale to extremely low times. So the first pulse, the pilot pulse, can be something like 200 microseconds, which is 0.2 milliseconds. So in 0.2 milliseconds, you want to inject a small amount of fuel and stop. Wait for something like another 500 microseconds or something like, and again start the main injection, again stop. And if you want to do 5 injections, you have to stop like this. So you can imagine how sophisticated the mechanical system and the electronic system has to be to respond to these small changes. We will see. So I hope the problem is clear, and how we are trying to solve the problem is clear. So now we will go back to the heat release, and we saw that reduction in the accumulated fuel during the delay period lowers NOx, lowers noise, but it will raise the smoke because diffusion will go up. Fuel accumulated during this period is controlled by the ignition delay. It can also be controlled by pilot injection, which is what we saw now. Now coming back to the pressure diagram, the same heat release has now been shown in the pressure diagram. This yellow line is the motoring diagram where there is no combustion, we are simply cranking the engine. This white one superimposed over yellow shows combustion. We started injecting the fuel at A, but till B there was no combustion. So A to B is called ignition delay. And at B we have sudden combustion, which is called premixed combustion up to C, sudden rise in pressure. That is what we saw in the heat release rate, as sudden rise in the heat release rate. Then we have a slower rise in the heat release rate, which we saw here, which is diffusion. So the pressure also rises slowly, and then we have the expansion process. So this is how the heat release rate gets transferred to the cylinder pressure, or cylinder pressure and heat release rate are linked together. Is it clear? So if you have an engine where the premixed is controlled, maybe we will have a pressure curve which will not go so sharp. It will go up like this and then come down, maybe something like this. It will not raise suddenly. So we will not have that explosive nature of combustion, which means that noise will come down, NOx will come down, and since diffusion is good, smoke also will come down. So in a modern diesel engine, we are aiming at noise reduction, we are aiming at smoke reduction, we are also aiming at NOx reduction. And all this we want to do without sacrificing efficiency. So this is the aim, and this is brought about in 2 ways. The first way is pressure, you boost the injection pressure, and second way is you have pulsed injection. So these two enable you to get this, bring about these benefits, and the pressure I told you is extremely high, and pulses also I told that they are very, very short pulses. So this is the main complexity. Now there are several injection parameters which can affect the performance of an engine. First and most important is the start of injection, when we actually start the injection. That controls efficiency. Then when we end the injection, we want to end the injection quickly. If you end the injection after a very long time, the efficiency falls. So end of injection is very important. If start and end are brought closer and closer, it only means that you have to pump at a high rate. So rate of injection becomes important. Then the amount of fuel that you inject becomes important. If you want high power, you inject high torque, you inject more fuel. The pressure at which you inject becomes important, and the droplet size and dispersion become important. In fact, if you look at these, all these are controlled by the injection system. The first 5 quantities are completely controlled by the injection system. The last one is a result of what happens. Droplet size and all, if the injection system produces high pressures, the droplet size is low. So the injection system can significantly affect emissions, efficiency and emissions, as we already saw. Now what kind of injection timing do we want? When we are running the engine at no load or idling, we want to inject the fuel very close to top dead center, sometimes even after top dead center or almost at top dead center. When we have a low load, slight load, we want to slightly advance the timing. When we have full load, we want to advance more. And if we use exhaust gas recirculation, we want to retard. If the engine is cold, we want to advance. So you find that injection timing has to be changed with respect to so many parameters. So injection timing itself is one of the most important parameters to be controlled by the engine management system. You have to keep on changing depending on what the engine wants. And the duration of injection could be something like 1.25 milliseconds. Total duration may be only that. It's a very, very short duration. And in that short duration, you have 2 pulses, 3 pulses or 4 pulses. So it becomes complicated. This figure shows how the fuel injection quantity has to be changed with respect to speed. In an engine, in a truck engine, let us say, if the driver has pressed the accelerator to the floor, he is not at all changing the accelerator and the vehicle speed is changing. This is how the injection quantity will change. When you are starting the engine, you may inject a very high quantity because just then only the engine will quickly start. After starting, immediately you will bring down the quantity. And afterwards, when the speed is raising, the quantity will be raised because the volumetric efficiency will raise. And at some point, the peak of volumetric efficiency will be reached, then you may want to bring down the fuel. And here, you may want to significantly bring down the fuel so that you can prevent overspeeding of the engine. So this is another control. This is speed-based control. So far we have seen only injection, but now it is speed-based control. So the injection controller has to control the quantity that is injected based on speed. At this speed, it has to permit this much of quantity. At this speed, it has to permit a lower quantity. Again, a lower quantity and very, very low quantities here. So with respect to speed, it has to continuously monitor the quantity. With respect to load and speed, it has to monitor injection timing. It has to decide the number of pulses. All this, and the driver doesn't know any of this. The driver only presses the accelerator. So the electronic controller has a lot of software in it, which keeps on checking all this and decides what to do to the engine. What injection pressure to set, what injection timing to set, what duration to set, how much quantity to allow. All this is decided by the electronic controller. Whether it should be 2 pulses or 3 pulses or what, all this is decided by the controller. So if you look at diesel engine control, these are the things which we can control. We can control speed of the engine. It is governing. So we normally study it as governors, where speed alone is controlled. Then we can control load, the torque of the engine. That means by controlling the quantity of fuel, and that is based on speed, as I showed here in this curve. We can also control combustion and emissions by controlling the injection timing, injection duration, injection pressure, injection rate. All these parameters can be changed, and by that also we can control emissions and combustion. So there are several things that the diesel engine controller can do, and in fact the heart of the diesel engine is the diesel engine's controller today, and the diesel engine fuel injection system. So without, and you know that it's considerably expensive. Nowadays, the common rail system has come in cars, which is very common in cars, and it's very soon coming in trucks and buses. And the common rail system itself is expensive. I'm not very sure, but I heard that it could be something like about 20 to 30,000 rupees for the injection system alone. So it's a pretty expensive injection system, whereas a conventional mechanical system would not be so costly. Now, we will first go to the first level of electronically controlled fuel injection systems. The first level of electronically controlled fuel injection system, which is even today used, is called the unit injector. The unit injector is a system which is a step above the conventional system because it can produce very high pressures. Now the unit injector basically has a cam which runs a plunger, and the plunger directly operates an injector. In fact, this tube which you see here is not a very long tube. It's a very short tube. It is inside the injector itself. So the plunger, this is the plunger. the plunger operated by the cam, the injector are all in one unit. They are basically one unit. And on the right hand side of this unit you see a solenoid operated bypass valve. And this is controlled by the electronic control unit, ECU, or the engine control unit. And the ECU receives several sensor inputs. For example, the driver's foot pedal, the engine temperature, the engine speed. All these could be inputs, coolant temperature, the atmospheric air temperature, the amount of air that is going into the engine. All these inputs can come to the ECU, and the ECU decides what to do to the solenoid operated bypass valve. Now if you look at how this works, when the plunger moves up, fuel will be pumped by the plunger, and this fuel will go to the injector and it can get sprayed through the injector. But you also have a bypass line which is controlled by the ECU. If the ECU keeps this bypass line open, fuel will not flow through the injector, it will simply flow back to the tank. When it closes this bypass valve, fuel will flow through the injector. So what happens is, as the plunger moves up, the ECU closes the solenoid valve. The ECU is actually closing the solenoid valve at the point where you want the first injection. It closes it for some time. Then the injection occurs through the injector. So it may close it for 200 microseconds to get the pilot injection. So first it closes and the pilot injection comes, then it again opens. Then it waits for some time, the fuel simply goes back to the tank, again the ECU closes the solenoid valve and again opens it. So you get two pulses. Is this clear? So the ECU is basically operating this solenoid bypass valve. Once it closes, injection occurs, immediately it opens it. And then again waits for some time, again closes and again opens it. During this entire period, the plunger is moving up. So this entire thing happens when the plunger is moving up. So if the plunger is moving up for, let us say, 50 degrees crank angle, within that 50 degree crank angle, you can open and close the solenoid any number of times. You can have injection. So this is, I would say, the first level of electronic control of a diesel engine, which is a significant level. And this system is still used in many of the very big engines. Very big engines use this. So there they will have the injector. The bottom of the injector is what is this shown here. The plunger will be on the top of the injector itself, and the cam will be over the injector itself. So this entire thing is one injector. I have just broken them into different pieces and shown you. The advantage here is very high pressures can be developed because you are directly supplying the fuel to the injector. So you can go to pressures of 2000 bar without any problem. The other advantage is you can have pulsed injection. You can open and close. But the only disadvantage is all the pulses have to occur within the time where the plunger is moving up. That means you have to have it only within the duration where the plunger is moving up. So this is one of the problems, one of the main problems. So you can have pulse injection, but where you locate the pulse, this is crank angle, this is injection. But where you have the pulse should be only within the 50 degrees of crank angle. This is one restriction, so people went to the next level. This is also used in some applications. But in the next level, as someone was also pointing out, this is the kind of injection that we want. We are moving towards this. There are many engines which are already operating like this. You want a pre-injection, which is the pilot injection. So x-axis is crank angle, y-axis is injection quantity. You can even call it as injection quantity or injection rate, anything. So you want a small injection first to occur, and that small quantity accumulates in the ignition delay period and burns and then raises the temperature. Then you want the big main injection. The big main injection is the diffusion controlled combustion phase, which is injected at high pressure and it burns. Then after that, many engines stop with these two pulses, just two pulses and that's all. But now the third, fourth pulses are all coming because of emission norms. The third pulse is what is called as advanced post injection. This advanced post injection is after the main injection stops, you again inject some fuel, and this is what is called as soot burning. That is, the main injection, diffusion combustion injection, produce some soot, some smoke, and that smoke should not be emitted. And if you want to remove that smoke, you burn that smoke in the engine itself. And to burn that smoke, you again inject some small quantity of fuel. That further raises the temperature and burns the soot particles inside. So this is called as advanced post injection, which is for soot burning. So this brings down the soot in the exhaust. And then you have a retarded post injection, which can occur even during the exhaust stroke. That is, you may even inject fuel during the exhaust stroke. And that fuel is not meant for the engine, it is meant for the catalytic converter. We may have a catalyst in the exhaust, and that catalytic converter needs hydrocarbons for reducing oxides of nitrogen. Do you get my point? Oxides of nitrogen have oxygen, and if you want to reduce it, you have to remove that oxygen. And to remove that oxygen, you use hydrocarbons. So you use hydrocarbons to remove that oxygen from oxides of nitrogen. So something like that. I am just giving you a vague picture of how it works. So this retarded post injection is to put some hydrocarbons into the exhaust pipe for the catalytic converter, not for the engine. So the diesel engine injection system is not only taking care of combustion inside the cylinder, it's also taking care of the after treatment device in the tailpipe. So it does all these injections and many more. As time passes, I think there will be more pulses also. So pre-injection, which is pilot injection, then main injection, then advanced post injection, and retarded post injection. It means the injector has to open and close so many times in one cycle. And some of them are of the order of microseconds. This will be in order of microseconds. This may be also in microseconds. Microseconds injection, microseconds gap. So you start, stop, start, stop, start, stop. So at least some 4 or 5 times. So how do we achieve such kinds of injection systems? And this obviously cannot be from the unit injector. Why? Because this entire duration will cross the upward movement of the plunger. You are working at durations that are very, very large, and the upward movement of the plunger is crossed. So we go to the common rail fuel injection system. The common rail fuel injection system, as you typically see it here, this is taken, I think, from a website, I think of Delphi. You see here there are many manufacturers of common rail systems. One manufacturer, important manufacturers are Bosch, Delphi, then Denso, then Magneti Marelli. So many manufacturers are there. So all of them, all these systems have some commonality. And if you learn one system, the other systems are similar. So you have a fuel tank, you have a supply pump. The supply pump takes the fuel from the tank and pressurizes it to very high levels. This is the one which pressurizes to 1500 bar. So this high pressure fuel is led into this common rail. The common rail is a long tube, and you push the fuel into this long tube at 1500 bar or 2000 bar, and there is a pressure limiter here. This pressure limiter sees to it that the pressure in the rail is maintained. If you pump too much of fuel, it drains off the fuel. So the electronic controller is controlling the pressure limiter. It is looking at this pressure. So you have a pressure sensor here. So continuously the controller is monitoring the rail pressure, and it adjusts the rail pressure to the level that you want, depending on the operating condition. And this high pressure fuel is allowed into each one of these injectors. So 4 injectors, the high pressure fuel is supplied to these 4 injectors, and the ECU controls the 4 injectors through these lines. Whenever it wants to inject, it sends a pulse to that injector, and now it sends 3 or 4 pulses to every injector in every cycle, and sequences and operates this. And the excess fuel from the injector comes back to the tank. The excess fuel from the pressure rail also comes back to the tank. So this is how the system works. It's a very simple system. In fact, it is simpler than the mechanical system. You simply pump the fuel into a rail and extract the fuel from the rail. It's like a reservoir, you are tapping the fuel. And the most important thing is the injector, where you control the injection process. So is this system clear? We will now go to the working of the injector, because that is the most important thing. Now the working of the injector is shown here. The injector, you see here, is somewhat similar to the conventional injector. I am not going to talk about the conventional injector, but in operation it is exactly the opposite of a conventional injector, but it resembles a conventional injector. I hope all of you know how a diesel injector works, isn't it? You have a needle which is pushed down by a spring, and high pressure fuel goes to the bottom of the needle from the pump, and the high pressure fuel pushes the needle up and then sprays. This is how the normal injector works, but this is not how the common rail injector works. It is opposite of that. So again I will tell you the normal injector. High pressure fuel only goes to the bottom of the injector, it never goes to the top of the injector in a normal injector. It goes to the bottom of the needle, develops pressure here, so the needle is pushed up, and when the needle is pushed up, fuel will be sprayed. And then when the pressure stops, the needle is pushed down by the spring and the injection stops. This is how the normal injector works. Now the common rail injector always has high pressure because the fuel is coming from the rail. From the rail, fuel is coming at high pressure into the injector. So always you have high pressure, and that high pressure is led to the bottom of the injector, and if it is led to the bottom of the injector will open, and it will always be open, which you do not want. So you also allow this high pressure fuel to the top and to the bottom. So fuel goes to the top of the injector and to the bottom of the injector, and the area on the top is more than the area at the bottom. So the net force on the injector will be downward. So in the common rail injector, the fuel, high pressure fuel comes from the rail here. From the rail, the fuel comes here and it is supplied to the bottom of the injector. That is, this is the needle of the injector. This is the needle of the injector. The high pressure fuel is supplied to the bottom of the injector needle and also to the top of the needle. And if you carefully observe, the area at the bottom of the needle is less than the area at the top of the needle. So this pressure pushes the needle down and this pressure pushes the needle up, but the net force is downward. And this net downward force closes the injector. The injector is sealed on its orifice. So the high injection pressure is used to seal the injector. It is not used to open the injector. In fact, this is very desirable. If you go to higher and higher pressures, it is very difficult to seal the injector because the injector will start leaking. Now you are using this high pressure itself for sealing. So if the pressure goes up, the sealing force also goes up. So it automatically gets sealed. So this is one. Now how do you open this injector? To open this injector, what we do is we relieve the pressure on the top of the injector but do not relieve the pressure at the bottom of the injector. Then what will happen? The net force will reverse itself and become upward and the needle will go up. So the needle is actually opened by the pressure difference. And this pressure difference is enormous because we are looking at 1500 bar. So very high pressure difference, very high forces, the needle will be immediately open. It will just open like a switch. So now you have to look at the solenoid valve. The solenoid valve is on the outlet which is attached to the top portion. So if the solenoid valve is closed, if it is closed, then what happens is nothing flows out of the injector. So fuel goes to the top, fuel goes to the bottom, nothing is flowing and the net force is downwards. It is closed. If you want to inject, you open the solenoid valve like it is shown on the right hand side. When the solenoid valve is open, fuel now starts flowing like this. It flows through this orifice and comes out. And this is an orifice. So what happens when flow occurs through an orifice? That's fine, that's the result. But in any orifice, if something flows, what happens? There's a pressure drop. So can I say that the pressure here will be lower than the pressure here? The pressure at B will be lower than the pressure at A when the orifice opens. So if the pressure at B, pressure at A is what is acting at this point also. Can I say that? So the downward pressure would be, the pressure at the bottom would be more than the pressure at the top. And this comes because of the orifice. So you need to have an orifice. If you do not have that orifice, the pressure will become atmospheric. Suddenly pressure at A and B, everything will fall. So you don't want the pressure at this point to fall, you want the pressure at this point to fall. So for that, in between them you put an orifice. And the solenoid valve opens and the pressure on top decreases, pressure at the bottom does not decrease. The net force on the needle is upward and the needle opens and the fuel sprays. And when you want to stop the injection, you again close the solenoid valve. When you close the solenoid valve, there is no flow through the orifice, there is no pressure difference across the orifice, both the pressures become same and the injector will close. So this is how the injector functions in a common rail engine. So I prefer calling this an electro-hydraulic injector. It is not an electronic injector. It is controlled entirely by the hydraulics. And what the electronics is doing is only controlling the solenoid valve. And mechanically it is very complicated. Imagine this entire needle has to move in 200 microseconds and come back. 200 microseconds is a very, very short time. Imagine the acceleration that it will experience. Suddenly it has to move and then it is come back. It moves only by 1 mm or so maybe, but still it's an enormous acceleration. And that enormous acceleration is got by the very high forces that are developed by the fuel pressure. So this is an electro-hydraulic injector. Of course, there are other kinds of common rail injectors which are completely electrical. There is what is called as a piezo injector, which is completely electronic. We are not discussing that. How the injector current looks. The injector current, typical injector currents for part and full loads. This is we have taken from a running engine in the laboratory. You can see how the injector current is on this side. If you can see, there is a raise in current, fall, and then a small this thing like this. Sudden raise, fall, and then like this. This is the current that is applied on the solenoid. This is the current given to the solenoid. So the current given to the solenoid, this is current is I, and this is time. Is like this, something like this. Raises, falls, and becomes 0. This is called peak, and this is called hold. So we call it peak and hold current. You give a very high current for a short time and then give a low current. This very high current is given for a short time to make the solenoid open quickly, and this low current is given because it is enough to hold the solenoid. So you give peak and hold, peak and hold. So you can see how complicated the electronics is also. Every time it has to give a peak, hold like that. So you can see here different operating conditions. There is an operating condition where there is only peak, and the pilot injection was 300 microseconds, if you can see that. And the main injection was something like, maybe if that is 300, it could be something like 800 or 900 microseconds. And in this case, the pilot injection was 350. So there is a peak and a hold, and the main is slightly smaller, again peak and hold. So this peak and hold are applied in every pulse. So if there are 5 pulses, each pulse has peak and hold. So this is the level of technology today. So this is peak and hold. This is so I just to summarize, if you take a normal diesel engine, the pilot injection, main injection will all be varying like this. On the x-axis, this is from a running engine which we have captured all this information. The x-axis is load, BMEP, brake mean effective pressure, and the y-axis is timings. You can see that the pilot injection timing is here, the main injection timing is here, the main injection duration is here, the pilot injection duration is here. All of them are varying. So the controller has to change all these parameters as the engine is running. So when the driver presses the accelerator, all these parameters will vary, and the injection system is continuously varying all this. So this is what we see here, even at a constant speed. And imagine what will happen when speed is also changing. There will be many more variables coming inside. So the advantages of the common rail system are, we go to very high pressures, even greater than 1500 bar. We have full control over start and end of injection. We have control over injection pressure, and injection pressure does not depend on speed. We have pilot, main, post, retarded post, so many injections possible. You have variable injection pressures, and most importantly, the system is modular. You can use the same common rail system, leaving the injector spray alone. You can use it for a wide variety of engines, because the pump, the rail are all independent of the engine. They are not very much linked to the engine. So you can use the same pump and same injector on another model. Only thing is you may have to change the injector. So there are certain things which are common. So it is modular, and that could bring down cost, and it brings down the emissions, noise, fuel consumption. So it is a it's a highly superior injection system, which has considerably changed the scene of diesel engines, as we all know. Now diesel engines make noise which is like petrol engines. And sometimes you are not even able to recognize whether this car, when you sit inside, it is a diesel engine or a petrol engine. So it has become that just because of this pilot injection. So I stop this portion here, and I want to move on to turbocharging. But if you have any questions in any of these, I'll answer.
Sir, what do we mean by the dispersion phase, the physical part of the ignition?
Yeah. So I think you wanted to know the diffusion phase, right? So if you look at the fuel injection, when you inject the fuel into the combustion chamber, let us say we are injecting at high pressure through an injector, so the fuel comes as droplets and it goes inside. Now a liquid fuel as such cannot burn. Fuel has to vaporize, mix with air and then only burn. So the first drop which enters has to first vaporize, move out of the drop, go and mix with air and then burn. So this is a physical, this is something physical, and vaporizing, mixing and all are physical things, they are nothing chemical about it. After it mixes, chemical reactions have to start, and that is totally chemical. So you have a physical delay, you have a chemical delay, that is clear to you. Now after this physical and chemical delay occur, combustion starts. When combustion starts, the temperature goes up. Now you are continuing to pump the fuel. So now the next part of fuel which is coming into an environment which is very hot. So it suffers very little physical delay, very little chemical delay. Immediately it starts burning. And now the fuel droplet does not vaporize fully, but it is ready to burn. So how can it burn? The fuel has to vaporize and it has to diffuse into air and burn. So that's why we call it diffusion combustion. So that combustion is not pre-mixed. You didn't give it time. You want it to burn immediately. It has come inside and it is ready to burn. And for being ready to burn, the vapor should be there, but it's still a droplet. So the vapor should come out of the droplet, mix with air, and all this have to happen fast. So the second phase of combustion is entirely governed by these phenomena. There is no ignition delay, but everything is governed by how quickly fuel can mix with air and burn. So we call it mixing controlled combustion or diffusion controlled combustion. So there, if you want to make it fast, you have to enhance these processes. That is, you have to move air vigorously, you have to make the fuel droplet very small. That is why we inject at high pressure.
So it's not the case in MPFI system.
MPFI we use volatile fuels and we are injecting it on the valve much earlier.
Air is coming from some other place.
No, here your air is coming, no, air is MPFI engine, first you inject the fuel on the valve.
Yes.
Then when the valve opens, air takes the fuel inside. But you have given lot of time for it to vaporize.
So there is nothing like diffusion phase.
There is nothing like, because it is homogeneous mixture. You are compressing and having a spark. So everything is pre-mixed here, but it is flame propagation. In the diesel engine, there is no flame propagation as such in pre-mixed. You mix some air and fuel, you are compressing it. So it suddenly burns.
And the pressure is only 3 bars in MPFI.
Because you are not injecting into the cylinder. You are injecting in the manifold.
So soup burning leads to red hot particles, then there may be burning more.
No, how this wood burning works is like this. In the diesel engine, you always use very lean mixtures.
Yeah.
We never use rich mixtures, so always there is excess air. Only thing is, the fuel droplet does not find this air. Because you have not mixed the fuel uniformly with air. You are just throwing some droplet into the engine. There is air, but this droplet did not find that air. So if it did not find that air, it produces soot. But then, after some time, it can find that air, because everything is moving in the cylinder. Let us say some soot was formed. The soot was formed because that fuel droplet did not find enough air. But there is air elsewhere. And if you stop the combustion process for some time, this soot droplet will move. And it will get into some region where there is air. But it will not burn because temperature is not there. So at that time, if you pump some more fuel, that raises the temperature and makes this soot to burn. So this is reburning that soot.
It remains in the cylinder or it comes out?
Inside the cylinder itself, soot is there, but the soot has moved to a region where it can find air. Again, you raise the temperature, the soot burns in that air. So it is burning inside the cylinder itself. So you burn the fuel inside the engine, so that it doesn't come out.
Sometimes it comes out, I think. I have seen.
No, with all this, what I am saying is, this is all done in the engine, but still soot will come out. That is next level. That is after treatment. So we do everything possible to bring down soot and NOx in the engine. And that was sufficient for some time. Even now it is sufficient. But in the next emission norm, that is not sufficient. You have to do after treatment. You put a trap or NOx catalyst or something in the exhaust. Because we are going to lower and lower emissions. People are saying that we are going to levels where it is difficult to measure. You are asking for a level of soot which is so small that I cannot measure and say that it is that much. We are going to the limits of instrumentation. And now people have started counting the number of particles. So the next level of norms is going to be with so many particles of soot coming out of the engine. It is not size, it is not quantity, it is number. So you need to have an instrument which will count. So it's coming.